Hi, I'm Dr. Stuart Midgley, CEO at Doug Technology. Just quickly, who's Doug? We're a seismic processing company that puts together high-performance computing and software and services and delivers it as a cloud. We do this through a number of offices around the world. We have about 30 petaflops of compute. But tonight we're here to talk about the A64FX CPU from Fujitsu. This is a 48 CPU ARM-based system running SVE or vectorization extensions to the standard ARM instruction set. These are single socket systems with about 32 gigs of HBM memory, and they deliver about 1 terabyte per second of memory bandwidth. I've got a photo a little later on, but you basically get the system we have is a 2RU box with 8 nodes inside, and it's running CentOS 8.2. And I've sort of just put a few little snapshots of the CPU information and how the memory and CPUs are structured on the socket. I'm going to sort of briefly talk about a few benchmarks that we run on various bits of hardware. One of them is a full waveform inversion, which is a large stencil 3D finite difference code, which tends to be memory bandwidth limited. I'm going to talk a little bit about our Kirchhoff time migration, which is mostly indirect memory lookups, and our DBlend code, which is FFT based. These will give some sort of indication of the performance of the CPU. But first, why we do this? Well, we're always striving for better tools to characterize the subsurface. Algorithms like full waveform inversion were first proposed in the early 80s, and in the 2000s, they started to become possible to actually run these styles of algorithms. In 2010, computational complexity still remains a limitation in running these. So even though we've gone 30 years, we still were limited by the amount of compute that we could get access to. But thankfully, compute power continues to increase. And today, we're actually able to run many of these complex algorithms. So better tools, better physics, we can now do these wave equation-based inversions and other algorithms, which are incredibly compute intensive. And here's a quick indication of what you get. So on the left, we have our Kirchhoff pre-stack depth migrated full stack, and we have sitting beside it the velocity model that was used to generate that migrated data. On the right, we actually have the model coming out of our high frequency full waveform inversion. So there's no imaging done here. And as you can see with this advanced algorithm, you can get nearly all the detail that you have in your image seismic in your actual model. And that's what we're now able to do on a regular basis. So let's talk about this high frequency full waveform inversion. It's called Doug Wave. It's based on DeVito. Many months ago, I actually ported this code to the Fujitsu A64FX CPU, and it wasn't that easy. We had mostly issues with Python. The environment was difficult. We had to patch DeVito, we had to patch Python. We couldn't get the auto tuning to quite work. So I had to sort of manually set the patch sizes to run inside the FWI. But with a couple of days work, sort of fiddling around, we're able to get it to run about 20% faster than our workhorse Knights Landing, where we've done most of the done a huge amount of optimization for. So when we got the new system in-house, I actually just went and downloaded the latest version of DeVito, and it compiled straight away, and I ran the benchmark, and out of the box, it was twice as fast as our workhorse KNL. If you look at the KNL CPU, it's got roughly 450 gigabytes per second of bandwidth, and the HBM and the A64 FX system has got roughly 1 terabyte per second of memory bandwidth. So 2x is roughly in line with what we'd expect for DeVito, DeVito being memory bandwidth bound. So this was a great start. We got a code up and running. Probably took, after we got the operating system installed on the compilers, probably took about 30 minutes to we were running the benchmark. Next, decide to tackle the Kirchhoff time migration. And this is part of a much larger suite of software. We call it Doug Insight. It's a huge processing package. It uses Java, C, all sorts of bits and pieces. So this was going to be a little more complex to build, but surprisingly, it went relatively easily. We had to work around some of the FFTW integration. So we sort of had to go and grab the Fujitsu performance libraries. We've got it to build after a couple of days, pretty straightforward with GCC and a custom build of FFTW. But unfortunately, it was slow. This was put down to the fact that we weren't getting any vectorization. The KTM, we'd programmed it to use AVX512 intrinsics, and when we took those out, basically, and left with the simple loops, the compiler wasn't able to vectorize it. So I went away and took the same code without AVX512 vectorization and built it on a KNL and ran that, and we saw that roughly the ARM CPUs were about twice the speed of a KNL, which was roughly in line with the gigahertz performance and the expected flops output of the KNL. Now, again, the KNL cores are quite weak. Without AVX512, they're not very fast, and so the fact that the A64FX had twice the memory bandwidth and stronger cores, it was about twice as fast. So we set about building with LLVM and the Fujitsu backend over GCC, and it didn't really make a lot of difference. Again, we have to do a bit of work, I think, porting our AVX512 intrinsics over to SVE. The compiler just doesn't seem able to vectorize the code that we have. So that's something which we're fiddling around a little bit with now, and we'll continue. The next code which we looked at was DBlend. Now here's a quick shot or slice through a shot, and as you can see, it's multi-source. So we've got a number of sources throughout the seismic, and our DBlend basically allows us to pull out one of those sources. And you can see it does a really nice job. This is a code which we're running a lot of now. It's very topical, so we thought we'd try and port that. Unfortunately, it's a little bit of work in progress. This is mostly an FFT-based code, so again, we had to fiddle around with the FFT implementation. In this particular code, we were using the actual MKL version of Fourier transforms. We weren't using FFTW interface, so we had to do a little bit of porting to get to an FFT library that's supported on the ARM CPU. We actually have it running and compiling. It's just producing incorrect results at the moment, so it's not really meaningful to give you any performance indication. We do think we're going to have a little bit of a problem with this code because whilst we've got some simple tests up and running incorrectly, our benchmark does require a fair amount of RAM and more RAM than this system has. So we started looking at ways we might be able to use swap or using the locally attached SSD to cache some data. But interestingly, what else did we do with it? We got this lovely little box in the office, and I thought we might as well play around with it. Here I've got a quick picture of what it looks like. There's the 2RU chassis, and you can see here that one of the sleds pulled out. So we've got this is actually 2 nodes. So it's 2 single socket nodes. You can see the 2 sockets sitting there in front of you. Of course, we do this thing called Mellanox Multihost NICs, which is a card and network that we sort of built with Mellanox. And we thought, well, I wonder if this will work. So we pulled the system apart, plugged in our multi-host NIC, built up the kernel drivers from Mellanox, and voila, the system happily works. And you can see on the right, I've got the output of ETH-tool. So our NIC is fully supported and sees out to 100 gig, even though at the moment it's just running at 50. So that was quite nice to see. Additional to that, we're actually now working with Fujitsu to see about immersing this node. So our aim is, once I've finished all my benchmarking, is to remove the fans from the system and dunk it into a tank of oil. So that'll be interesting and something to look forward to. So just quickly wrapping it all up, we're roughly seeing performance in line with our expectations. Again, the system's got twice as much memory bandwidth and about the same number of flops as our workhorse KNL. So codes which are memory bandwidth limit are going twice as fast, which is great. I was really impressed with the ecosystem around the CPU. You had all the tools you expect. It's bog standard CentOS/Red Hat Linux, everything you like builds and runs. It's great that you can actually program this device on the A64FX on a $40 home device or a Raspberry Pi. When I did my initial port, I was actually doing a lot of the system-based compiling and building on a Raspberry Pi and then copying them across to the device. I'm running ARM-based systems in laptops and desktops. The Mac Mini I have on my desk now is an ARM-based system. So the total ecosystem of the ARM environment is really coming along and is quite impressive. It's great that it runs standard Linux, and you can just use GCC and LLVM. This makes it really easy to deliver Python, NumPy, Git, everything that you need in a good development environment. One little downside to the system that we're seeing, and our benchmark of the DBlend will potentially have a problem with this, is the lack of large amounts of memory. So each node's got 32 gigs and you can't upgrade that. So we have been experimenting with using the NVMe drive in the M2 slot. At the moment, we're seeing about 1 gigabyte a second, maybe 1.2 gigabytes a second of bandwidth to that NVMe drive. So there's some potential there to use it as a fast cache. But overall, it's a really simple system to use. We've had probably 4 or 5 of our internal staff using it, and most people forget that they're actually on an ARM-based system and try building on an x86 box and copying the binaries across, and of course they don't work. But they've forgotten that it is an ARM-based system. Everything's just standard Linux and is really nice. And it's great to see that Fujitsu shifted their compiler backend to LLVM, which again makes it really simple to support. Finally, if anyone wants to find out a bit more about Doug or contact us regarding what we're doing with the A64FX, here's some contact details. Thank you very much.